Okay, so we are looking at a tutorial on session 7. And here we're going to be looking at matrices, right? And of course, vectors. So we're going to see how we could flow with that. So the first thing we're going to look at in matrices would be matrix multiplication. And in matrix multiplication, there are a couple things we need to look at. The first thing, which is item 1 here, is that matrices could only be multiplied if certain conditions are met. And the matrices, the two matrices to be multiplied, in order for them to be able to be multiplied, they must be such that the number of columns in the first matrix must be equal to the number of rows in the second matrix, right? So the number of columns in the first must be equal to the number of rows in the second, right? That's the first thing. The second thing we need to know when we're doing matrix multiplication is that the order of the resultant matrix will be the rows in the first by the columns in the second. And that will be the order of the resultant matrix. The third thing we need to do is to understand that to do the multiplication, we must multiply the number of, we must multiply rows by columns. So the process is multiplying rows in the first matrix by columns in the second matrix. And the fourth thing we need to be aware of is that when we are filling out the matrix, right, we've always fill in the elements of the new matrix from left to right, top to bottom. In other words, like how you're going to be reading a book, right? So our first example, example 1, says that if we have the matrix A and B, A being this matrix 2, 3, minus 5, 4, B being this matrix minus 5, 1, 0, 2, and we multiplying them, or we say finding the product of the two matrices, then the first thing we have to do is to see if the matrices could be multiplied. Now, in order for that to happen, the columns in the first must be equal to the rows in the second. So this is a 2 by 2 matrix, meaning that there are 2 rows, 1, 2, and 2 columns, 1, 2. Similarly, B is a 2 by 2 as well. So the rows in the first will be 2. The columns in the first matrix will also be 2. The rows, or the number of rows in the second matrix, is 2. And the number of columns in the second matrix is 2 also. So we need to identify firstly if they could be multiplied. And they can be multiplied when the number of columns in the first matrix is equal to the number of rows in the second matrix, which means this number here and this number here must be equal. So if you look at it, you will see that this is in fact so, right? The number of columns in the first matrix is going to be equal to the number of rows in the second matrix. That means they can be multiplied. So we are all clear there. We also know that the order of the resultant matrix is the rows in the first by the columns in the second. So the rows in the first will be this one. The columns in the second will be that one. So when we combine these two, right, that tells us that our resultant matrix, when we do find the product, or we do multiply these two, will be a 2 by 2. So this resultant matrix here is going to be a 2 by 2, which means they're going to have 2 rows, 1, 2, and 2 columns, 1, 2, right? So we know it's a 2 by 2. When we do this calculation, this multiplication, we have to fill in the elements in this new matrix here, right? From left to right, which means left means starting here, moving this direction. And we must do the top and then go to the bottom. So this is going to be the first, moving from left to right, first and the second, and then when we finish, we go down to the next one, the bottom row. So then we go left to right again. So if this is the first and this is the second, then the third element will come here, and the fourth element will go there. Okay, so this is the process of filling out the matrix, and it's done in a manner as if we were going to read, like if we're reading, right? Left to right. So this first matrix here, this first element here is going to be formed by doing a multiplication, whereby we multiply the rows of the first by the columns of the second, or rows by columns. So that means we're going to multiply this row here, 2, 3, by this column, minus 5, 0. So we multiply in 2, 3 by minus 5, 0. Right? That's what we're going to do. So let's do that. Right? So 2, that's the row element, by minus 5. Right? So that's what we're going to do. So 2 by minus 5, right? Two by minus 5, right? Plus 3 by 0. So let's see how we came up with that. 2 by minus 5 plus 3 by 0. That'll be giving you this one. The next one will come here, but that'll be this row by this column now. So we're gonna try to get that done. Right? So we have to multiply the 2, 3 by the 1, 2 now. Right? So let's do that calculation. 2 by 1, right? Plus 3 by 2. Okay, that's what's going to go in the second one. So now, if you notice, we would have finished multiplying this row by both columns, this one and this one. So the next thing we have to do is go now and multiply this row by the two columns. So we have to take off right? So we're going to multiply this row here now, the minus 5, 4, by minus 5, 0. Those two there, right? So let's do that. So going to be minus 5 by minus 5, right? Plus 4 by 0. Okay, so that's where we read so far. Taking my time and going through it slowly so that we could make sure and get it correct. And then the last one will be the same row here, this minus 5, 4, but we're shifting from this column to this column now here, the 1, 2 column, right? So let's get that done. Right, so we're going to multiply the minus 5 by the 1. And then we're going to multiply the 4 by the 2. Right? So in that case, we would have done all of the multiplication required, multiplying rows by columns. So let's see what we get when we do that. What is going to happen here is that the top one, which is this one here, 2 by minus 5 is minus 10, plus 3 by 0 is 0. So minus 10, right, plus 0 is going to give us minus 10. So we're going to end up with minus 10 on top here. Okay, so that's going to be the first element. Let's do this next one here, right? 2 by 1 is 2, plus 3 by 2 is 6. 2 and 6 is going to give us 8. So that is going to give us this 8 here. Let's go to the next one, which is this here. Minus 5 by minus 5 is plus 25. And 4 by 0 is 0. So we're going to have 25 from here, 0 from here. 25 plus 0 is 25. And then finally, we're going to have minus 5 by 1 is minus 5. 4 by 2 is 8. So it's minus 5 plus 8. And minus 5 plus 8 is going to give us 3. So our product, A times B or AB, if you multiply A by B, you could write it as AB, right? It's going to be minus 10, 8, 25, 3. So, right, so I took my time to give you all the calculations necessary. In example 2, this looks a little different from example 1. Now, by far, the most common multiplications of matrices you get would be 2 by 2 matrices being multiplied. Now, some people, they forget that because they constantly multiply 2 by 2 matrices, they think that matrices could only be multiplied if these are of the same order. In other words, 2 by 2 by a 2 by 2, or 3 by 3 by a 3 by 3, and so on. But that's not true. What is required is this first situation here. This one. They must be such that the columns in the first, the number of columns in the first matrix must be equal to the number of rows in the second. So sometimes when I give this question here and I ask, can this matrix be multiplied? People tell me no, because this matrix and this matrix, they are not of the same order. But that is not the requirement for matrices to be multiplied. It is the requirement for matrices to be added or subtracted, right? They must be of the same order, but not for multiplication, right? For multiplication, the requirement is that the number of columns in the first matrix must be equal to the number of rows in the second matrix. And that's the case here. These two numbers here are the same. This one here is the number of columns in the first. This one here is the number of rows in the second. And if you notice, these two numbers are equal. They are both 2. So because these numbers are the same, they are both 2, it means the matrices are compatible and they can be multiplied. So observing that, we say, right, we know we're going to end up with a valid matrix. And what is the order of the matrix? So let's go back here. The order of the resultant matrix is the rows in the first by the columns in the second. The number of rows in the first by the number of columns in the second. So the number of rows in the first would be 2. And the number of columns in the second will be 1. This is the number of rows in the first. This is the number of columns in the second. So it means that we're going to get a 2 by 1 matrix. We're going to get a 2 by 1. Now, a 2 by 1 matrix will look just like this one. This is a 2 by 1 because there are 2 rows, 1, 2, and 1 column. So we're going to end up with a 2 by 1 as well. That means you're going to get something at the top, another element at the bottom. Now, this first element is going to be made up of this row by the only column. So 1, 2 by 4, 1, which means that 1 has to be multiplied by 4 to give us 4. And then 2 has to be multiplied by 1 to give us 2. So that's what is going to go at the top here. To get the bottom element, we're going to multiply this row by this column. So it's going to be 3 times 4, which is going to give us 12. And then 4 times 1 is going to give us 4. So that this here will be the resultant matrix when we work it out. So let's work it out. The top one will be 4. Right? The top one will be 4 plus 2, which is going to give us 6. All right? So that's going to be this top element. And the bottom one here, 12 plus 4, is going to give us 16. So this is our final answer. Right? This will be the product C times D, CD. Okay? Again, don't forget that it does not have to be the same order. Unlike here, where it's the same order, these are of different order. This is a 2 by 2, C's are 2 by 2, and these are 2 by 1. But they could have still been multiplied because the condition is that these two numbers must be the same. That is to say, the number of columns in the first matrix must be equal to the number of rows in the second matrix. All right? Don't forget that. That is an important thing. So you might see that in your multiple choice, right? If you do encounter that. Another thing that we need to be aware of is something called equal matrices, right? Now, equal matrices says that if two matrices are equal, all right, of course, they must be of the same order, then corresponding elements must be equal. So if in this demonstration of equal matrices, if they tell us that this matrix is equal to this, and we have to solve for x and then y, then we could equate corresponding elements and work it out from there. All right, there's a mistake here. Let me fix it. Let me just fix this. This should be -4, and this here should be 5. Right? Okay. So if these matrices are equal, then this element here, x plus 2, must be equal to this one here. Right? The first element in the first row on the left must be equal to the first element in the first row on the right. So x plus 2 must be equal to -2. The second element in the first row on the left must be equal to the second element in the first row on the right. So -4 must be equal to -4. Okay, well, that's obvious. Wouldn't really help us though. The first element in the second row on the left is 5, and that must be equal to the first element in the second row on the right, and 5 equal to 5, right? That's correct as well. Y minus 6 must be equal to 6 because this is the second element in the second row on the left, and it must be equal to the second element in the second row on the right. So this must be equal to this, right? So what we are saying is that x plus 2 must be equal to -2, and y minus 6, right, must be equal to 6. And that those relationships will help us to solve for x and y respectively. So let's solve for x, right? So I'm going to write that x plus 2 must be equal to -2 by equating corresponding elements on the left and right in the top row. And of course, that is going to tell us that x is equal to what? -2 minus 2, right? By minusing 2 on both sides, it means that x must be equal to -4. All right, and you could always try it back. If you put -4 here and you add 2 to it, you're going to get -2. Let's work out the next one. What's the next one? The next one was this one. Y minus 6 must be equal to 6. So let's work out that. Y minus 6 must be equal to 6. So if y minus 6 must be equal to 6 from equating these two, it means that y must be equal to 6 plus 6 by adding 6 here and here. Or some people say bring the -6 over and change the sign. So that is saying to us that y must be equal to 12. Good? So we were able to solve, right, for x and y, utilizing the fact that corresponding elements must be equal if the matrices are equal. All right, so you can use that pattern for equal matrices if you have to solve. Now, there are 3 main points that you need to be aware of when coming to do the 4th step that you are supposed to be aware of. Okay, and let's see what those 3 main points are. Well, the first one is that the determinant of a matrix A is written as A with 2 vertical dashes on it, all right? And we are assuming that our matrix A has elements A, B, C, D. This is a general form of a 2 by 2 matrix. So if we want to find something called the determinant, which you need to know, right? It is written like this, and the determinant of A is A, B, C, D with these 2 vertical lines on either side. And what it means is that you find the product AD and you minus from it the product BC. In other words, you multiply these 2 numbers and subtract from that answer the product of these 2 numbers, right? That's how you get the determinant. The adjoint of a matrix A, sorry, or A adjoint, right, is written as A adjoint like this. And to get that, what you do is you interchange these 2, A and D. D comes where the A is, and the A goes where the D is. So you get D here and A here, like this. All right? The next step to get the adjoint of A or A adjoint will be to multiply this and this, both of them, by -1. A shortened way of calculating that answer, B by -1 and C by -1, is simply to change the sign on the original number. So let's say B was 2 then the answer in the adjoint will be, B will now become -2. Let's say C was -4, then in the adjoint, right, C will become 4. All you do is you change the sign, but that's equivalent to doing this multiplication, all right? The next thing you need to know, very importantly, is how to find the inverse of a matrix A. And that is written as A to the -1. And how you find that inverse is you take 1 and put it over the determinant, or you find the inverse of the determinant, right? Put 1 over the answer that you would have gotten when you did this calculation. And then you multiply that by this adjoint that you would have calculated. That product, that calculation here, gives you something called the inverse of a matrix A. So these are important things you need to be able to do to be able to handle the next very important step, which is the solution of linear simultaneous equations using a matrix method, right? You need to know how to do these 3 items here. But besides these 3, to do this part here, there are 2 other little things you need to be aware of. The first one is that you must learn that if you have a product like matrix A times matrix X, and it is equal to a third matrix B, then if we want to get matrix X, all we have to do is find the inverse of this matrix A and pre-multiply B by it, or multiply it in this fashion here. So you have to memorize this, right? That is one of the items you need to be able, in addition to the first 3 that we just studied here, to be able to solve a linear simultaneous equation using a matrix method. The second thing you need to know, besides these 3 items here, the second thing you need to know, in addition to those, would be, in order to make your life easy, one of the steps in this calculation is that you have to multiply a matrix by 1 over the determinant. This is really supposed to be the determinant, right? Right, so this part here, this calculation here, you have to do that last. Don't do that up front, because if you do it up front, it will make your working a little more cumbersome. So this is the second thing you should know about when you're doing these calculations. So let's say we want to apply this knowledge to this question where you were asked to solve 4x minus 5y equal to -6, 3x plus 2y equal to 7, given that these 2 equations hold. Solve this simultaneous pair of linear equations using a matrix method. Okay, so let's see how we would go about doing that, right? And they could start this question from any position, but this would be the most involved process that you could encounter. In other words, starting from the 2 raw equations, move all the way through to the end. Sometimes they could start it from position, different positions, and you have to recognize it and be able to move all the way through. All right. Having said that, if we start off with 4x minus 5y equal to -6 and 3x plus 2y equal to 7, then the first step is to break this up into this matrix product here. In other words, the 4, the -5, the 3, and the 2 form this equation, this matrix here. The x and the y form this matrix here, and that must be equal to -6, 7, which will give us the third matrix. So whatever are the coefficients, you would extract those coefficients or numbers in front of x and y, form one matrix, x and y would form the other matrix, and on the other side, the answers would form a third matrix. We call this one here A, we call this one here X, we call this one here B. And we go back to our previous knowledge. Well, of course, if this is A times X equal to B, if we have to find X and Y, which is the process that we need to go through when we solve in a simultaneous equation, that's not the process, but the aim, right? If we have to find X and Y, which we call X, then we have to solve this equation for X. And I just mentioned to you that one of the additional things you need to learn besides the first 3 is this relationship here. If AX equal to B, then X must be equal to A to the -1B. So similarly, if AX equal to B, then X will be equal to A to the -1B. So that's how we're going to work out, right, our X and Y values, which we call matrix X here. How do we get the inverse right? How do we get this? Well, from up here, item 3, the inverse of a matrix, a to the minus 1, is obtained by putting 1 over the determinant of A and multiplying it by the adjoint. So that's what we're going to do. We're going to find this inverse here by putting 1 over the determinant of A and multiplying it by the adjoint of A, or A adjoint. The determinant is AD minus BC. So 1 over the determinant will be 1 over AD minus BC. Let's check back determinant again. Determinant is AD minus BC. So 1 over the determinant will be 1 over AD minus BC, right? The adjoint is, let's go back and look at adjoint. Interchange A and D, right? So A would come where D is, D would go where A is, like this, and multiply these two by minus 1, or simply change the sign on the original numbers. So let's deal with that. AD in this matrix here, matrix A, is what we're interested in. This is A and this is D. So AD will be 4 times 2, which is going to give me 8. Minus BC. This is B and this is C. So we're going to minus, this is this minus here, B times C. This is minus 5 times 3 is minus 15. So we're going to minus 15. Right? So this minus is this. And when we multiply B by C, we get negative 15. So this is what AD minus BC is going to look like. And of course, minus is equivalent to plus. So this is going to be the same thing as 8 plus 15, which is going to give us 23. So 1 over the determinant of A is 1 over 23. So that's part of our calculation for A to the minus 1, or the inverse of A. We still have to do the adjoint. Adjoint is very easy. As we learned, we're going to interchange A and D, right? So this is going to be A down here. Let me just make this a little bigger. Right? So we're going to interchange these two. So 4 is going to go down here and 2 is going to go up here. So 4 came down here, 2 goes up here. Right? So that's the interchange. And then multiply these by minus 1, or change the sign. So minus 5 is going to become plus 5. And 3 is going to become minus 3. Right? So this is what is known as A adjoint, which we carry down here. Now, if you simply had to calculate the inverse of A in your exam, you would then take this and multiply it by each one of the numbers, 1 over 23 times 2, times 5, times minus 3, and times 4. And of course, reduce the answers to the lowest fraction possible, simplest fraction possible. And that would give you an answer. But we have a secret. We're not going to do this now. We're going to actually take into account this second note, which says that we multiply by the 1 over the determinant last. So we're going to multiply by this part here last. We're not going to do it now here. We're going to do it last, or lastly, right? So we're going to take this A to the minus 1, which we got to be 1 over 23 times 2, 5 minus 3, 4. We're going to take it and we're going to substitute it right here. This A to the minus 1, which is 1 over 23 times 2, 5 minus 3, 4. Right? This part, we're going to put it here. 1 over 23, 2, 5 minus 3, 4. Right? That is coming in here for A to the minus 1, which we just calculated here. That comes in right here. And then we're going to put B in there. What is B? B is this one. B is minus 6, 7. So now, to get X, which is really X and Y, that's the objective of our calculation, we have to work out this. But as I said, we're going to multiply by this part here last, right? We said that that is the last thing we're going to do. Whenever you have to do a simultaneous equation, you're going to multiply by this lastly, or last, right? So notice I'm not multiplying it by this as yet. I'm going to multiply these two first. So I'm multiplying a 2 by 2 by a 2 by 1. So I'm going to end up with a 2 by 1 answer. 2 rows, 1 column. How do we get that answer? 2 by minus 6 is minus 12. 5 by 7 is 35. Remember, we multiply in row by column. So 2 by minus 6 is minus 12. 5 by 7 is 35. So that, when we add this, that will give us our first element. Let's get the second element by multiplying this row by this column. So minus 3 by minus 6 is plus 18, which is this. And 4 by 7 is 28, which is this. So we're going to add these two together to get this element here. Minus 12 and 35 will give me 23. And 18 and 28 will give me 46. So we end up with this final calculation for x. And here, you'd notice how nice they designed it. So that now, lastly, let's go back, multiply by this, which is this part here, the 1 over determinant of a, which is the 1 over 23. We're going to do that last, right here. We're not doing it before. We're doing it at this point. So 1 over 23 times 23 is going to give me 1. And 1 over 23 times 46 is going to give me 2. So it means that our x matrix x is 1, 2. And of course, matrix x, if we go back up, is xy. So if matrix x is xy, then this calculation we did here is xy. That means that x must be equal to 1 and y must be equal to 2. So x must be equal to 1, y must be equal to 2. Okay? So this is how we go about doing our solution of a linear simultaneous equation, right? Noting that 1, 2, 3 items must be learned for that, as well as these two properties, all right? This is a property, but this is a technique here so that we make our work easier for ourselves, all right? So that will be our matrices. Any questions there so far, guys, or you're okay?
Be okay, sir.
Okay, all right. Cassie, all right?
Yes, sir.
All right, great. All right, so the next thing we're going to look at is some vectors, right? And vectors are always present, and there's no difference. I expect it to be very present in your multiple choice as well, those who are doing the exam this year, right? So we're looking at vectors, and in order to understand vectors, right, very quickly, you must know that there are two types of quantities. One is a scalar and one is a vector. Scalar quantities are those that have magnitude only, like distance and speed. And vector quantities are those that have magnitude and direction, like displacement and velocity. The scalar quantity distance is the magnitude part of the vector quantity displacement. And similarly, speed is the magnitude part of the vector velocity. So in displacement, you must have distance and direction. So you can say that the distance between two objects would be a distance of 10 meters, but then you need to put a direction, right? You could say in a direction due north, or you could say on a bearing of 30 degrees, right? Or you could state it relative to another known vector, right? But in a vector quantity, you must not only say the magnitude, but you must also put a direction in there, right? So that's where vectors come from. Now, a vector could be considered as a translation or a slide. And we had to learn this equation previously, and it's a very important equation. It keeps coming back all the time. And what it says is that if we have a start point and we add some form of translation vector to that start point, we could end up at an endpoint, right? And this formula, of course, you need to learn and commit it to memory. Start point plus translation vector equal to endpoint. So let's look at a couple examples that they could ask you in your exam. So if they tell you vector P, which is equal to 3, 4, translates a point A21 to a point B, right? They could say, based on that information, find these coordinates, all right? Find these coordinates. And you have to be able to deal with that. But the answer is quite simple. The answer is quite simple because, right, in this answer, we are going to use the equation that we had, right? What is the equation? The equation is start point plus translation vector is always going to give us our endpoint. All right, so that's what we're going to use, which is this equation here. All right. So what is our start point in this question? That's what you always have to ask yourself. And you could find it here. This vector P is translating A to B. So A would have to be our start point and B would have to be our end point. So we could put that in here. A would have to be our start point, right? B would have to be our end point. And our translation vector, therefore, it would be P. All right? So we could put in some stuff here. All right, let's see what we could put in. A, which we know is 2, 1, we could put in 2, 1 here. Now notice I changed the format from a coordinate format for a point to a, which is horizontal, to a vertical format, which would represent the components of a vector. So this A here is really a vector that we are representing. And that vector, once you take it directly from a point, is known as a position vector because it tells you the direction to point A starting at the origin. And once you start at the origin, that vector is known as a position vector. We'll mention it again later on in vectors tonight, all right, or this evening. Let's see what else we have. We have the translation vector P, which is 3, 4. So we're going to write that in. And we're going to end up with a position vector for B. We wouldn't get a point right away. We'll get a position vector for B, which is known as OB. All right, so that's what is going to give us our answer here. So let's work that out. Let's work it out. This 2 is going to be added to this 3. So you're going to have 2 plus 3. And this 1 is going to be added to this 4. So you're going to get 1 plus 4. And the answer we get is going to give us the position vector OB. So let's see what happens. 2 plus 3 is going to give us the answer on top here, which is going to be 5. Right? And 1 plus 4 is going to give us the answer on top here, which is going to be 5 also. So our answer for our position vector OB is going to be 5, 5. But notice they did not ask us for the position vector of OB. They asked us for B's coordinates. That means we have to convert our component form of the position vector OB to the coordinate or horizontal form for the point B. So that means that we write it in this manner. And only when you do that, you're going to get your full marks at this point. If anything other than that, you wouldn't get your full marks, all right? So remember to do that conversion. So that's one way they could ask you about vectors as a translation. Another way could be as in example 2, whereby here they give us that vector A translates a point P to a point Q, right? Find the coordinates of the start points. So again, they didn't tell us, well, which one of these is the start point. You have to figure out what is the start point. All right. Now, it's kind of obvious because they give you A, they give you Q, and the only thing they didn't give you was P, and they asked you to find the coordinates of something. So it looks as if this is going to be the start point, but we could go a little further and reason it out. So let's start off by always remembering our translation equation or vector equation for translation, right? Which is start point plus translation vector is equal to end point. The start point here in this case is P because this vector is translating P to Q, the start point to the end point. So our start point is going to be P. So I'm going to put P up here. Our translation vector is going to be A. And our end point is going to be Q because you're going from P to Q. Okay? But remember, these are vector equation. This is a vector equation. So the vector that represents P would be OP, and for Q will be OQ. Right? So let's see what we can come up with. So for OP, that will be here. We don't have anything for that. Right? So we could write it back, OP. For A, we have a value minus 2, 5, so we could put that right there. So let's put it in, minus 2, 5. And for OQ, right, we have this, minus 1, 2. We just have to put it into this vertical format, right? So what we would notice is we're missing this guy here, the OP is the one that we are missing. So what we're going to do, is work out what OP would be. So OP could be found by taking the minus 25 and bringing it over on the other side and changing the sign. Or some people say minus the vector minus 25 from the left and do the same thing on the right. So what is going to happen is you're going to still have the minus 1, 2 here. But on this side, you're going to be minusing minus 25 like that. Okay, so let's go through that process, right? This minus 1 minus this minus 2 is the same thing as minus 1 plus 2, because minus minus is a plus. And if you take minus 1 and you plus 2 on it, you're going to end up with 1 as your answer. So 1 is going to come up here. Okay, now remember, you're not going to have your calculator there to do that calculation. So you're going to have to be able to work out this part here, right? This minus 1 minus minus 2, which becomes minus 1 plus 2, which is going to give us this 1 here. And then 2 take away 5. Obviously, 2 take away 5. Let me just check something. Yeah, 2 take away 5 is going to give us, let's now, did I make a mistake here? No, right. So let's double check it. 2 take away 5 is going to be negative 3. All right, so that's 2 minus 5 is minus 3. So it means then that the value for P, right, if this is the position vector OP, written vertically, to get the coordinates of the point P, which will be the coordinates of the start point, we just have to change it to that orientation, right? So to get our answer for the coordinates of the start point, which would have to be P, this would be the answer here, 1 minus 3. So this would be our final answer, okay? And then thirdly, right, they could give us one of this type. Now notice that we had to get coordinates of 2 different items here, right? We had to get coordinates for P, and in the first one, we had to get coordinates as well, right? In this one here, we had to get something slightly different, right? In this one here, we had to get the coordinates of B. In this one, you have to get the coordinates of P. And in this one, you have to write K as a column vector. So that wouldn't be coordinates. If you have to write a vector, that would be column vector would be vertical components. So let's see what we have here. We have vector K translates the point X to the point Y. Write K as a column vector. The common thing in all of them is that we're using the same starting formula, right? Start point plus translation vector equal to end point. So our start point here is going to be X because it's translating X. And we are using K to do that. And we're going to end up with our end point, right? Which is Y. Right? So let's remember that that has to be OX and this has to be OY because position vectors. So what are we going to use for OX? We're going to use minus 2, minus 1. Minus 2, minus 1. Translation vector, well, that's K. We don't know what that is yet. So I'm just going to put back K. And for OY, that'll be 3, 5 written vertically like this. Okay. So we are interested in finding K as a column vector. So K is going to come back here. But we need to remove this, right? So we minus it from this side, and we're going to have to minus it from this side as well. So this side started off with 3, 5, and now we have to minus it on this side here. So it becomes minus 2, minus 1. Of course, we have to be very careful when we're doing the calculation because you have negative numbers involved, right? And there's no calculator. So if you're doing multiple choice, right? So it'll be 3 minus minus 2, or simply 3 plus 2. All right, and 3 plus 2 is going to give us 5. So that's what's going to go up here. There's going to be 5 minus 1, which is going to be 5 plus 1, which is going to be 6. In this case, we do have to convert it to a horizontal form because they wanted it as a column vector, which means vertically like this. Okay, so our answer is going to be 5, 6 written vertically. Now, in order to do a lot of the questions that come up with vectors, right, you really need to know some vector properties, right? And some of the vector properties is what we're going to be studying right now, okay? So the first property we're going to study is what are equal vectors? Well, the vector AB and CD are equal vectors because not only are they going in the same direction or parallel as stated via looking at these two arrows. Once you have arrows like this on two vectors, it means they are parallel. But these two vectors are equal in magnitude. How do we know that? Well, it looks so, but more importantly, they tell us that by putting these two dashes here and here. It could be single dashes on both of them or 3 dashes. Once they have the same number of dashes on both, it means that they are equal in magnitude or size or length. So that tells us that the vectors are equal because it satisfies the two criteria for vectors being equal, which is they are equal in direction, or they have the same direction or are parallel, and they are of equal magnitude. So vector AB is equal to CD. This is one property you need to know about. So that is property 1. Second property you need to know about is something called inverse or negative vectors. Inverse or negative vectors. Right, just 1 second. Right. So we're looking at inverse or negative vectors, right? And if you look at these two vectors, right, these two vectors are what we call inverse vectors, right? One is going in this direction, the other one is going in the opposite direction. But if you have a look at them closely, you'd realize that not only are they going in opposite direction, they are parallel, but going in opposite direction, and they are equal in magnitude. So you need to have those qualities to make them inverse or negative vectors. So for example, CD and BA are what we call inverse or negative vectors because CD is going this way and BA is going in the opposite direction. So they are inverse or negative vectors. DC and AB. Look at AB. Look the direction it's going in, right? That's AB, and look at DC, opposite direction. So DC and AB are inverse vectors. Let's go across here. AB and BA are inverse vectors because AB is going one way and BA is going in the completely opposite direction. CD and DC. CD is going this way and DC is going in the completely opposite direction. So we say that they are also inverse vectors. Now there's a property that we need to know about inverse vectors, right? The property is that if we have a vector AB and we establish that AB is an inverse vector to DC, like here, DC and AB are inverse vectors, then one is the opposite of the other one. See? So this dash here means is opposite to. So AB is opposite to DC. They are inverse vectors. Similarly, DC is opposite to AB. They are inverse vectors. AB is opposite to BA because these two are inverse vectors. DC is opposite to CD. So think of the negative as opposite. Easy word to remember. The more advanced word is inverse or negative, right? Vector. So that's the second property you need to be aware of to do calculations for vectors. Let's look at the third property here, right? Multiple of a vector, right? Anytime we could show that two vectors are related, whereby one is a multiple of the other, like how this, both of them are parallel here, right? Because we see in the arrows. But this one is smaller than this one, is shorter, right? But they are parallel vectors. Now, in our exams, once you could show that one is a multiple of the other one, then that is proof that they are parallel. So if I could show that CD is some multiple of AB, then it shows that they are parallel. Or if I could show that AB is some fraction of CD, right, then they are parallel. So for example, in this case, CD might be, if K is 2, right, then CD, if you could show that CD is 2 times AB, then they would be parallel, as an example. This 2, it could be 2, it could be 3, it could be 5, anything. Once you could show that there's a multiple. Or if you could show that AB is equal to some fraction, let's say 1 over 2, a half of CD, then they are parallel. AB and CD are parallel. So this is a third property you need to be aware of. A fourth property, which you have learned about before in your handouts and so, which I'm going to remind you about, is this one, right? Which is important. It says that whenever one vector is a multiple of another, right, and there is a point common to these two vectors, that is lies on these two vectors, then there is collinearity. What does collinearity means? It means that 3 points lie on the same line. So let's see what that means in vectors, right? Example, if AB is a vector, you know this little dash means a vector, and you could show that AB is a half times BC, then if you notice B is common, right? You're seeing B here and here, right? So not only are you showing that there's a relationship where one is a fraction of the other, one is a multiple of the other, like how we were saying here, but if you notice, there's a common letter. B is common here and here. Across here, there's no common letter. C, D, A, B, no common. A, B, C, D, no common. But here, B is on the left and B is on the right. So if you could show that one vector is a multiple of another one, and there's a common letter on both the left and the right-hand sides of the equation, then B is a common point and A, B, and C are collinear. B is a common point and A, B, and C are collinear, meaning they all lie on the same line. Another example of collinearity, just to give you a frame of reference, is if I could show that BD is equal to 2 times DE, you notice that you're seeing D here and here. It's common. Here B was common, right? Here D is common, look. So once I could show that, what it would mean is that B, D, and E are collinear, that is, they lie on the same line. Or another example, if we show that LM is a third LQ, right? This doesn't have to be a whole number, it just has to be any number, right? So if LM is some number times LQ, right, some factor, then not only are these two vectors parallel, this relationship shows collinearity. That is, 3 points lie on the same line. What are the 3 points that would lie on the same line? L, M, and Q. Here, B, D, and E would lie on the same line. Here, L, M, and Q lie on the same line. How do I know that? Well, there's a common letter on both sides, L here and L here. And once you could show a relationship like this, and there's a common letter on the left side of the equation and the right, then there's collinearity. That is to say, 3 points lie on the same line. In this case, the points would be L, M, and Q. In this case, it would be B, D, and E. In this case, there's no collinearity because there's no common letter on either side. There's no collinearity here because there's no common letter on both sides. All that is happening here is that this vector is parallel to this one. Okay, so that's what you need to know. So there are 4 properties that you need to be aware of. Property 1, 2, 3, and 4. 1 is equal vectors. 2 is inverse or negative vectors. 3 is multiple of a vector. And 4 deals with collinearity. That is points lying on the same line. Now, with vectors, just like with normal numbers, right, or scalars, you need to know how to add. Scalars are easy. Just add like if you're adding numbers. vectors are not so easy. You cannot just add vectors like if you're adding numbers, because vectors have direction to take into account. But at your level, right, and for your exam, you need to know how to add vectors. And there are two ways that they point out to you. The first way is the triangle law, and the second way is the parallelogram law, right? That's the second way. The first way, which is the triangle law, if we're adding two vectors, right? That first one, which is a triangle law, we use that for two vectors going either clockwise or both going anti-clockwise. Once they are both going clockwise or both going anti-clockwise, then we use the triangle law. All right, so what is that all about? Let's see. Right? Now, the sum of the two vectors, if they are both going clockwise or anti-clockwise, we use the triangle law. And to get the sum of the two vectors, which is known as their resultant, right? When you add two vectors together, the sum that we get is known as the resultant, is found by connecting the start or tail end of the first vector to the end or arrow end of the second vector. All right, so let's look at that across here. In this question, in this example, they wanted us to determine the resultant of the vectors A, B, and BC, shown in the diagram below. So this vector here is AB, right? This one here is AB, and this vector here is BC, all right? So this is equal to BC, and this one here is equal to AB, all right? And they want us to add up the two vectors, add up this one and this one together. Now they are both going, if you look at them, one goes so, one goes like that. And if we take it as it is going, right, it will be tending to go in a clockwise direction. Both of them go in a clockwise direction. If one was going so, and the other one was going so, like that, they would both be going in an anti-clockwise direction, because if I did like this, right, take the natural course of it, that'll be anti-clockwise. So I could use the triangle law to add them up as well. So what is the resultant or the addition of these two vectors? What do I get when I add them together? All right, well, this is AB and this is BC. Let's see what AB is. AB is, if we go from A to B, that means we move one across here, right? One across here, and then we go two up, 1, 2. So this is 1 across, 1, 2 up. So this vector AB is 1, 2. Let's look at the vector BC from B to C, right? Starting from B, we go 1, 2, 3, 4. That's this 4 here. And then we go 1 up to get to C. So to get from B to C, we go 4 across and 1 up. So that's how we get BC as 4, 1, right? Now, if we have to add these two, right, that's not a problem. I could actually add them together and get my answer by saying 1, 2. Sorry. 1, 2 plus 4, 1. Right? And what would I end up with? I would end up with 1 and 4 on top would give me 5. And the 2 and 1 would give me 3. Right? So I could add it directly like that if I had the components. Right? And I would get an answer 5, 3. So I would know that the resultant, which is A to C, that's resultant, would be 5, 3. Right? So if I add vector AB plus vector BC, I will equal with the resultant AC. In other words, I would have started at A and ended at C. So the resultant will be AC, which is this. Right? So that's one way to do it, directly adding it like that. But if we had to do it using a diagram, right, what we could do is follow the rules that we had on this side, right? What was the rules again? The rule says that in this triangle law, for these two vectors going, in this case, going clockwise, the sum of the vectors, which is known as their resultant, would be found by connecting the start or tail end of the first vector. This is the first vector, and this is the tail end. So we have to connect that to the end or arrow end of the second vector. This is the arrow end or the end of the second vector, BC. So we have to connect these two from here to here. So this direction here would be the direction of the resultant vector, which is A to C, right? And having gotten this, then we could measure and get the components. So let's measure. Start at A and go to C. Horizontally, or the X movement would be 1, 2, 3, 4, 5, right? And then vertically, it will be 1, 2, 3. So the components of the vector AC would be 5 in the X followed by 3 in the Y. So by drawing method, we get the same answer here as you would have gotten here using a calculation method. All right, 5, 3. So that's a very important skill that we just discussed. Now, the vector AC is equal to the resultant of AB plus BC, as I wrote down here, and we did it up here as well. And there's something else you need to know about. It's called the modulus. Now, what does a modulus or magnitude mean? The modulus or magnitude means the size of the vector. Because remember, vectors have a magnitude or size and a direction. And this is also known as the modulus. So if I have a vector AC with the little dash on top telling you that is a vector, and I want to find the modulus or magnitude or size of this vector AC, then that is written as or is equal to the vector with this dash on top with two vertical lines, one on either side. That is the symbol for modulus or size of the vector. Another way of writing this is just simply to take the dash off of it. So just take this dash off and you get the modulus. So you could write modulus like this, AC, or you could write it like this, the dash on top with two vertical lines on either side. Now, how do I calculate the modulus of a vector, of this vector and then any vector? Well, it's easy. The modulus of a vector or this vector would be the square root of 5 squared plus 3 squared. Where am I getting that from? Well, this is 5 and this is 3. Now, if you look carefully, this is a triangle. And we could apply really Pythagoras Theorem to get this distance here, which would be the magnitude or modulus of AC. And that's where this formula comes from. Pythagoras Theorem tells us that the square on the hypotenuse of a triangle is equal to the sum of the squares on the other two sides. And from that relationship, if we want to get the magnitude of this hypotenuse, we could find it by using this formula, right? That comes from Pythagoras' theorem. So the modulus or length or size of the vector AC would be the square root of 5 squared plus 3 squared. This is 5, this is 3. 5 squared plus 3 squared. And that works out to be 5.83 units. So if I were to do a scale drawing and I were to measure this, I would end up with this as my answer, 5.83 units as my answer. Now, this comes from Pythagoras theorem, as I said, to help us to work it out. But I'm giving you a nice little equation here, which is under a note. It says that the modulus of any vector, it doesn't matter what type of vector, it could be a position vector, it could be a displacement vector, any vector. Once we know the x component and the y component, we could get the modulus of this vector by using this formula. That is, we square the x component, we square the y component, we add them together, and we find the square root. So like in this case here, for AC, the x component was 5 and the y component was 3. Look, we have it here as well. So if we want to find the modulus or the size of that vector, all we do is to square the x, which is the 5 squared, look at here. We square the y, so we square the 3, look at here. Add them together, and then we find the square root. That will always give us the modulus. So this little note here, right, this little note here is quite important, and you should bear that in mind and learn it well. Now, all vectors require us to know that there is a magnitude part, which we just learn how to calculate, which is called the modulus, and a direction part, which is going to tell us how this vector is moving, in what direction. All right. So we know that for directions, right, we talk about angles. And in this, I'm going to draw an angle here for you. I'm drawing it in now. And let's call that angle theta, right? So let's say I knew the magnitude of this vector, but I wanted to get the direction. One way of stating the direction would be to get this angle theta, which would be the angle that the vector makes with the horizontal line, right? So how could I get this angle theta? Well, if I look at this vector, I know the opposite side to it here is this distance here, which would be 3. And I know right next to the adjacent side right here is 5. So basically, I know opposite and adjacent. And if this is a right angle triangle, this A to C and come back like how my arrow here is going, that's a right angle triangle because there's a right angle here, right in the corner here, because this is a vertical and this is a horizontal. Then to get this angle, I could appreciate that I have the opposite and I have the adjacent in a right angle triangle. So that means that I could use tan theta. So I could come down here and say that the angle between, to get the angle between AC and the horizontal, which I just drew theta, this angle up here, I could use the fact that tan theta is opposite over adjacent. So I'm going to make it a little smaller so you could see it a little better, right? Tan theta is opposite over adjacent. So I could work out this angle theta by saying, using this relationship. So I could say that tan theta is 3 over 5 because 3 is the opposite and 5 is the adjacent. So 3 over 5. So that's not a problem. If I have tan theta is 3 over 5, then I could get theta by saying inverse tan of 3 over 5, right? But in this case, you would have to put it on our calculator. In your exam, you wouldn't be able to do this calculation because you don't know this, right? But it's something that you need to know in general, because if you're doing paper 3, you could also get questions of this type. So theta now would be, when you find the inverse tan of 3 over 5, you get approximately 31 degrees if you round it to the nearest degree. So that's one way of getting the angle that would represent, right, this angle here that would represent a direction. Another way of stating this direction of this of that resultant AC, another way of getting that would be to state a bearing, right? So bearings could also be used, right? And or you could state a direction relative to another known vector. Okay, so let's summarize. When you have vectors, all right, you can add them together using 2 methods. The first method we learned is the triangle law, and that is used when both vectors are going clockwise like this one, or anti-clockwise. For example, one going like this. Where 2 vectors, if we look at their path, we could say that this would be going anti-clockwise, whereas this is going clockwise. Good. And in order to add them together, we could do it directly like this, or we can use a diagram like this. You get the answer in component form, like 5, 3 in this case. And you could find the magnitude or modulus of the vector by using this formula here, where we square the x component and the y component, add them and get the square root. That would give us the modulus or size of the vector, which is written as the vector with 2 vertical lines like this. In this case, it was 5.83 units. And also, you may be asked to get the direction. One way of stating the direction is relative to the horizontal. And in that case, tan theta would be opposite over adjacent, which is always the x component over, sorry, the y component over the x component. In this case, it's opposite over adjacent. And then we can work that out, right? Of course, if tan theta is 3 over 5 using this relationship, theta will be the inverse tan of that, which gave us 31 degrees in this case. But remember, there's only one method of adding vectors. You're supposed to know another method called the parallelogram law. So how do we know if to use the triangle law, which we just did, or the parallelogram law? Well, anytime you have 2 vectors that start from a common start point, like in this case here, right? Then we simply complete the associated parallelogram, And to get the resultant, we join the common start point to the opposite vertex. So let's say you had a situation like this where you had these two vectors. If you notice, there's a common start point here. That common start point is at Q. One vector, QP, is going in this direction, and the other vector, QR, is going in this direction, right? They both start at the common start point Q, right? So how would you go about finding the resultant of these two vectors, right? You cannot use the triangle law like we just did because they are not going in a clockwise or anti-clockwise direction. Here, they are both starting from a common start point Q. And therefore, we have to use the parallelogram law. How do we use the parallelogram law? Well, the first thing we need to do is to complete the associated parallelogram. That means to say, if we are seeing 65 degrees here, we have to come up with the other side of this parallelogram, which would be coming up here and then going across here, right? So we could get, if this is 65, we could get, measure 65 here, right? So we extend here, measure 65, go in this direction, and then draw our parallelogram going up like that, okay? Whatever the length of this, we would have to get that length on this side. Then, when we get that point, all we have to do is join here to here, and we would complete our parallelogram. Now, that's the first step. Once we complete the parallelogram, then to get the resultant of QP and QR, what we would have to do is join the common start point to the opposite vertex. So we'd have to join this point here to this point over here with a straight line. And that would be our resultant. Okay? So over here, right, we went through and we actually did it in detail, right? But what is instructive here is to note that scales are important. Scales are being used. So what I did was to show you that, all right, if the scale is 1 centimeter representing 1.5 meters per second, right? And we wanted to draw out QR, because remember, we have to do a scale drawing to be able to get our answers. We have to recognize that if the scale is saying 1 centimeter is representing 1.5 meters per second, if we have to represent 9 meters per second, then we have to realize that if, let me write it here, if this is the 1 centimeter is representing 1.5, right? What you realize is that this side here is always smaller than this side here. So this side is the length that you have to use to draw, and this side here is the actual speed in meters per second, right? So if our speed in meters per second is 9 meters per second here, that's what I have to write on this side, 9 meters per second. But I have to realize that I have to get this value here that I have to measure when I'm drawing it. How long do I make this? Well, this side is more than this side. This side is a factor of 1.5 times this side. Or, meaning I have to multiply going this way. If I have to go in the other way, I have to divide. So to get the value that I have to place here, right here, I have to divide this 9 by 1.5 to get this. So 9 divided by 1.5 will give me 6 centimeters. So basically what that is telling me is that I have to draw here at 6 centimeters long, which I would have done. Then I would measure 65 degrees with my protractor. And then how long would this go? Well, we know that this is supposed to be 3.75 meters per second, right? From on this side, right? This is 3.75 meters per second right here. So I have to get that on this side. How do I do that? Well, the same thing that I did to get this. I divided this by 1.5. I have to divide this 3.75 meters per second by 1.5 to get the length that this had to be drawn. That will give me 2.5 centimeters. So I would then draw this 2.5, right? And once I get these two, I would proceed as I described here to draw out these other two and then connect the common start point to the opposite vertex. Having done that, now I have the resultant. but I have to convert that to this unit, meters per second. So what would I do? Well, if when I measure this with my ruler, I get 7.4 centimeters, right? I'm going to go back to this side here and look at the relationship. If when I draw this out on my parallelogram, I get 7.4 centimeters. Let me write it down here. 7.4 centimeters. Then what do I write on this side to get the answer that this is relating to? Because they don't want the answer in centimeters. They want to know what is the resultant in meters per second, right? Because remember, we started with 9 meters per second here, 3.75 meters per second. They want to know what's the resultant, right? And to get the magnitude of this, or the modulus, we measured it. We got 7.4 centimeters, but what is that in meters per second? Now, if you notice, the relationship between this side and this side, as we said, is a 1.5 factor. So to get from here to here, we have to multiply by 1.5. And if we were going in this direction, we divided. Now, we have to go this direction, so we have to multiply. So to get the answer here, we'd have to take 7.4 and multiply it by 1.5. So that's why you see me multiplying 7.4 by 1.5 to get 11.1 meters per second, which would be this the modulus of this vector, or the velocity in this case, is 11.1 meters per second. So what would go here would be when I multiplied 11.1 meters per second. But remember, that's just one part of the answer, because they don't only want the modulus here, right? They also want to know what is the direction. Remember, all vectors have to be stipulated in not only in modulus or size, but direction is important too, right? So if they wanted us to get the angle, all we would have to do is measure the angles using the protractor. So I could have measured here and I would have gotten 18 degrees. So the resultant QS, right, would have a magnitude of 11.1 meter per second, or modulus, and it would be at 18 degrees to the vector QR. Or it would have been 47 degrees measured with my protractor from the vector QP, all right? And so on. So you could state this angle relative to all different things, right? In this case, we did it relative to the horizontal vector, or the starting vector QR, and then we also could do it relative to the vector QP. It all depends on what they ask you, all right? So those are known as, those are the two ways that we could add vectors together that you are supposed to be aware of. There are other things that you need to be aware of. For example, you are supposed to know what a position vector is. You are supposed to know what a displacement vector. You are supposed to know what is a unit vector. So let's describe and discuss these. The position vector we had discussed earlier when we were doing some of our calculations with translation of vectors, right? And what are position vectors? Well, firstly, these vectors always start from the origin, all right? So for example, if I drew a point here for you, P, right? Let me make this a little bigger. Right, so this is P. And to get to P, I go 1, 2, 3. 3 units in the X. And then I go 1, 2, 3, 4 units in the Y. Right? The coordinates of P would be 3, 4. Right? That's coordinates. But the position vector of P, which means start at O and go directly to P, that position vector would be called OP. Right? That line there, that vector. And that vector would mean that I'd have to still move 1, 2, 3 in the X. And then I'd have to go up now, right? 1, 2, 3, 4 in the Y. 3 here and then 4 there. But to write OP, right, I would have to write it 3, 4. That is known as the position vector of the point P. It's written vertically. So the position vectors always start from the origin, like this, what I just drew here. The components of these vectors are the same as the coordinates of the associated points. In what I give you here, the position vector of P would be the same 3, 4, but written in component form. It'd be vertical like this, as opposed to the coordinate or horizontal form for the point P. So I give another example. If you had a point P 10, 5, that would be the coordinates here. You would have a position vector OP, where this 10, 5 would be written vertically like this, right? So that's what position vectors are about. Displacement vectors, right? These are vectors that do not start from the origin. So an example or examples of displacement vectors would be AB, BC, GH, etc., where you notice the starting point is not the origin. In this case, the starting point is A. Here it is B. Here it is G. Unlike the position vectors, the starting point is always at O, which is what we said here, O being the origin. So that's position vectors, that's displacement vectors. What about unit vectors, right? Now, the main thing that you need to know about unit vectors is that unit vectors always have a magnitude or modulus of 1 unit. So the unit vectors that you are principally, or that you learn firstly, right, about, that unit vector that you learn firstly about is these two here, right? Those are the unit vectors for what we call I and J, right? I and J, these are what we call the principal unit vectors that you meet firstly, right? In some textbook, the vector I is called A and the vector J is called B in some of them. Or in our textbook, we would mainly see these here. And the vector I has these components, 1, 0, and J has the component 0, 1. All right, so you could always draw those out and see what these are. But the main thing about unit vectors is that they have a magnitude or a modulus of 1 unit. Now, you guys, I just give you a hint on how to find the modulus of any vector. And to find the modulus of any vector, if this is the x and this is the y component, you may recall to find the modulus, right? The modulus means take the vertical lines on either side. That tells us to find the length of that unit. What you do is you square the y, the x, sorry, 1 squared, which is this. You square the y, which is 0. You add them together and you find the square root. If you do that with these two components, which are the components for the unit vector I, you're going to get an answer of 1. That's what makes it a unit vector. Because a unit vector is one whose modulus or magnitude or size is 1. Right? The same thing for this vector, this prime vector J, unit vector J, which is sometimes called B in some textbook. Its components are 0, 1, right? And the modulus of that would be written like this. Two vertical lines, J, the modulus of the vector J would be these two vertical lines. And you do the same calculation. Square the x, 0 squared, square the y component, 1 squared, add them up, and find the square root. If you do this calculation, you'll get 1 as well. So those are the two principal unit vectors, I and J. But there are two others, maybe secret ones, a lot of people don't know about these two that you could be aware of or should be aware of. And we call them P and Q, right? Now, the components of P are 0.8 in the X, 0.6 in the Y. For Q, it's the reverse, 0.6 in the X and 0.8 in the Y. But what makes them unit vectors is when you find the modulus of the vectors, which is like this, modulus meaning the size or the length of the vector. How we do it? You square the X component, you square the Y component, you add them together, and you find the square root. What you would find is that the answer is 1. Similarly, for this one, if you do the same thing, you get the answer of 1. So these are the unit vectors you are supposed to be aware of, right? I, J, P, and Q. I is 1, 0. J is 0, 1. P is 0.8, 0.6. Q is 0.6, 0.8. Those are the unit vectors that you need to know about, and all of them, the modulus would be 1. That's what makes them unit vectors. Now, I've seen multiple choice questions like this, whereby you are supposed to know that if you have a vector whose components are given to you as x and y, then it could be written out like this: xi plus yj. I being one of the unit vectors, j being another of the unit vectors. That's these vectors here, right? So sometimes they ask you, they could say, write 3, 4 in this form, right? And you have to know 3, 4 would be, this is the x going here, and this one is the y going here. So 3, 4 could be written as 3i plus 4j. And they could give you this and say, write it in this format. And as multiple choice, they could give you A, B, C, and D, where this is one of the options, and you have 3 other options. So you have to be able to pick this out. Similarly, let's look at this one. If they tell you, write 5 minus 2 in this form here, then you have to know that this is the same thing as 5i, and this is minus 2j, right? This is the format that you need to be aware of. Or in your exam, they could reverse it. Instead of giving it a component form and tell you write it in the form of unit vectors, right? They could actually tell you to do the reverse. In other words, vice versa. So they could give you this and tell you write it in component form. So you know this 3 goes on top, this 4 goes below. Similarly, write this in component form, 5 goes on top, minus 2 goes below. Very simple once you know the pattern. Right? Now, they have a particular way of asking vector questions, and because of multiple choice, they could ask you some very simple ones, but you have to know certain basic things. One of the basic things you have to know about, all right, when solving vector questions, right, is really this one, this understanding, but this is your rule that they put in your textbook, right? So this here, and this is really the same thing. But the one on the right-hand side, which is this one here, is what the textbook states. And the one on the left-hand side is what I tell you to help you to understand it a little better. All right, and let's see what this says here. It says to find any vector, it does not matter the path that you take. All that matters is that you start at the same start point and end at the same end point. Okay, and I'll show you that in the question that is coming up, the example question. In the textbook, they have it in this way. They say in a polygon of vectors, which means a number of vectors connected to one another, the sum of the vectors in a clockwise direction is equal to the sum of the vectors in an anti-clockwise direction. So this is textbook, and this is me explaining it in a different way, right? So let's expand here and talk about this a little bit, right? So in this example here, right, let's look at the example. They say ABCD is a rhombus, right? So this is a rhombus here, ABCD, whose diagonals intersect at O, right? I didn't draw the diagonals in here, I drew it in later on here, right? O. But we're not talking about that yet. Let's talk about ABCD is a rhombus whose diagonals intersect at O. Also, the vector AB is equal to A and BC is equal to B, all right? So let me fix this up a little better. That's a vector AB is equal to A and BC, right, is equal to B. Right, good. So this is some information that they told us. They want us to prove that the vector AC is equal to A plus B, right? That's not a problem. Let's look at the solution here, right? If they wanted us to prove that AC is equal to A plus B, right? AC, right, is a vector that starts at A and ends at C. So that's one way of getting from A to C. But according to the language that I gave you earlier, right, it doesn't matter the path that you take. All that matters is you start at the start point, which is A, and you end at the end point, which is C. So I'm going to show you what that means. So if they want to get AC, I could go directly, or I could go from A to D and then D to C, or I could go from A to B and B to C. Now I'm going to choose to go from A to B and B to C because I already know what the vector AB is. They gave me AB up here as A. So AB would be A and BC would be B. BC would be B. So to get from A to C, which is this vector AC, all I have to do is go from A to B and then from B to C, because I'm going to start at the same start point A and end at the same end point C, right? Regardless of which path I take. Whether I go straight across, whether I go down and across, or whether I go across and down. I'm going to use this one, AB, which is a vector A. AB is a vector A. And then I'm going to go down, which is a vector B. Right? So I've just proven that the vector AC is equal to A plus B. And that's the first thing that they wanted me to show, right? Prove that AC is equal to A plus B. And that's what we just proved there. AC is equal to A plus B. Now remember, when you do a proof, you usually write these arrows in like this, like so, right? Because that tells you that I've proven what you asked me to prove. Okay, so that is the first one. The next one is express in terms of A or B, or both A and B, the vector AD, the vector CD, and the vector BD. So let's work on the vector AD first, right? Let's work on the vector AD. So AD could be obtained by going from A to D directly, or I could go AB, BC, CD, right? There are multiple ways. It doesn't matter the path that you take. So that's one way of looking at the question. Another way of looking at the question is to realize that this is supposed to be a rhombus. And in a rhombus, right? How do I know it's a rhombus? Because they told us that from the beginning, right? They say ABCD is a rhombus, right? So you're supposed to know certain properties. One of the properties of a rhombus is that opposite sides, like for example, AD and BC, right? Opposite sides in a rhombus, they are parallel and they are equal in magnitude, which means that the vectors would be the same because that's the properties for equal vectors, right? The properties for equal vectors is that they must be equal in magnitude and parallel. So the vector AD must be equal to the vector BC, okay? So I'm going to use that property to help me find the vector AD. AD must be equal to BC because they are parallel sides in a vector in a rhombus. So that means that BC, right, which we know as B, will be the same thing as AD. In other words, AD will be the vector B. Very simple. AD equal to BC equal to B. And we could put a reason. What's the reason? Opposite sides of a rhombus. Right? Opposite sides of a rhombus must be equal and parallel. That means the vectors must be the same. So if I know this is B, then this also has to be B. So that's that one. The next one we have to find is CD. So let's look at CD. Look at CD here. CD is going in this direction. That means that CD is in the same direction as BA. Now, we do not know BA right away. We know AB. But there's a property that relates BA and AB. The property that relates BA and AB is that they are inverse vectors, meaning that they have the same magnitude, but they are going in opposite directions. So that's what I wrote here. CD, which is what they want us to find, is the same vector as BA, right? Because they are opposite sides of a rhombus. CD is the same thing as BA. CD going this way, BA going this way. But we do not know BA, we know AB. But the relationship between BA and AB is that they are opposite. So BA is the opposite. Remember this negative here means opposite. So BA is the opposite of AB, right? And what is AB? AB is the vector A. So BA, in terms of the vector B and A, BA will be the opposite of the vector AB, which is minus A. Because remember, AB is A. So the opposite of AB will be the opposite of A, which is minus A. So that is saying that CD is minus A. So that's the second one. The third one, let's go back and see what the third one said. The third one says work out what BD is. So let's go and see what BD is. Look, BD here. Okay. So I could get from B to D in more than one way. One way is to go directly. So I could write that BD. BD is that. And I could get it by going down here and then going across here. Because it doesn't matter the path that you take. All that matters is that you start at B and end at D. So I can go down like this and go across. So if I go down, that will be the vector B, because they told us that. And we calculated that CD is the vector negative A from up here. CD is negative A. So BD will be BC plus CD, which is B plus minus A or B minus A. B plus minus A or B minus A. So BD is B minus A. So we did this one as well. The last thing we had to do here was show that OA is equal to negative a half into A plus B, and this one as well. So let's deal with OA as negative a half into A plus B. But what is O? If we go back up here, we say that ABCD is a rhombus whose diagonals intersect at O. So we have to recognize that we have to join the diagonals. That's one. So we need to join the other one to locate where O is. That's right here, right? So we drew it in here. These two diagonals are going to intersect at O, right? And what we have to do is prove that OA is negative a half of A plus B. OA is negative a half of A plus B. That's what we have to prove, right? So look at it. Look why OA is. OA is from O to A, going in this direction. But there's another property that you need to know about rhombuses. So you have to study the properties of quadrilaterals, right? And that as well is in your sessions. So what is one of the properties of a rhombus? Well, one of the properties is that the diagonals of a rhombus bisect one another. That means it cuts, the diagonals cut each other in half. So it means that OA, right, the length of OA will be a half of the length of CA, right? Notice I'm going in the same direction, right? I didn't say OA is a half AC, right? I said that OA is a half of CA because if we're talking vectors, you must be considering the direction, right? So I wrote that down here. OA, the vector OA, is equal to a half of the vector CA. Now, CA and AC are inverse vectors. So I'm going to write CA as the opposite of AC. Why am I doing that? Because I had calculated AC somewhere up before, right? Did I calculate AC somewhere before? I'm supposed to have. A plus B is C. All right, look at here. AC is up here. We have AC from part A as A plus B, right? So AC from up here is A plus B. So remember that, eh? AC is A plus B. I'm going to write it here because we got that from above. AC, that vector is A plus B. Good? But if they want us to find OA, which is a half of CA, which is the same thing as a half of the opposite of AC, because these are what we call inverse vectors, then this half is here, this opposite is here, or negative sign, and AC we had calculated from above to be A plus B. So I wrote it here, A plus B. So this AC will be A plus B, which is this A plus B here. This minus sign is this minus, this half is this half. So when you multiply a half by this minus, which is really minus 1, it'll be minus a half A plus B, which is what they wanted us to prove. That's why we put these double arrows. We were asked to prove that OA is minus a half of A plus B. From here, show that OA is minus a half of A plus B, and we did it. OA is minus a half of A plus B. We have done the proof there, okay? The last one they wanted us to prove is that 5 OD is 5 over 2 into B minus A. So what we're going to do is work out OD, and then the answer we get, we're going to multiply that by 5, and we'll see if we get this answer. If we do, well, then we would have proven what they asked us to prove. So let's work out OD by looking at our diagram again, right? OD now is going like this. OD, that's OD. But OD is a half of BD. Notice I didn't say OD is a half of DB, because for vectors, you must look at the direction. So OD is going down this way. So I have to look at the vector going down this way. So OD is going to be a half of BD. So I write that down. OD is a half of BD. Did we calculate BD before? Because what I've found, and I'm passing it on to you, is that as you go further in the question, they tend to ask you questions that relate to what you would have done before. And you might have done part of the calculation that you need now before. So I'm looking to see if I have BD anywhere before. So if I go up, it's not here. It's right here. I got BD here to be B minus A. So I'm going to use this for BD right here. So this is a half of, what is BD again? BD is B minus A. So I'm putting it here, B minus A for BD. Good. So that's OD. So I now know OD is a half of B minus A. But I'm not interested in OD really. I'm interested in 5 OD from up here. So we're going to multiply this by 5. So 5 OD will be 5 times this. This dot means multiply. 5 times this. So that'll be 5 times whatever we got here, which is a half into B minus A, a half into B minus A. So that 5 times a half will be 5 over 2 into B minus A, which is what they wanted me to prove. 5 over 2, 5 OD, sorry, is 5 over 2 into B minus A. And here we have it. 5 OD is 5 over 2 into B minus A. So we would have proven what they asked us to prove, right? So that is what your vectors is going to look like. I went through the main points, and now we're just going to close off with the beginning of transformation. So what is a transformation? A transformation is basically a movement, right? And the transformations we are going to learn would be translations, rotations, enlargements, reflections, right? And something called a glide reflection, which is a combination of a translation and a reflection taken in any order. But to close off tonight's tutorial, we're going to look at a translation or slide. Now, we encountered that before, so it's nothing really new. A translation or slide always is governed by this equation. Start point plus translation vector equal to end point. But when we talk about it in the context of transformations, right, a translation start point is normally called the object point. The translation vector is still the translation vector, and the end point is usually called the image point. Good? So let's say we had to translate the figure ABCD by moving each point by the vector 3, 4. That means we're going to slide each one of these A, B, C, and D according to this vector 3, 4, which when you translate it to this representation for a vector, it means move each one 5 units at an angle of 53 degrees to the horizontal. That is the same thing as moving 3 units in the X followed by 4 units in the Y. Let's explore that a little bit here, right? If we had to do that by a adjoint method, they would have either given us the points A, B, C, and D, and we had to plot it, or they would have given us the diagram already. In this case, it looks like they drew the shape for us. So A, B, C, D, right? A is the point 1, 3, right? So A would be the point 1, 3. See, I wrote A here. B would be the point, let's check out B. B is here, right? So B would be the point 3, 3. So that's B, right? So B would be the point 3, 3. So let me put it up here. So B is the point 3, 3. Let's look at the point C. C would be the point 5 across in the X, 1 up in the Y. So 5, 1, that'll be C. And D would be the point, let's see, let's look at the D's here. So D would be the point 1 in the X followed by 1 in the Y. So D would be the point 1, 1. So D would be 1, 1, right? So I wrote down A, B, C, D in this matrix. It's called the object matrix, by the way. So I could write it down here for you so you remember, right? This is a nice way of doing these questions. This is called the object matrix. And the object matrix is made up of the coordinates of the points on the vertices of the object, right? Taken and written vertically like this, right? Now, if we had to translate this shape by the vector 3, 4, see, vector 3, 4, it's equivalent to moving all of them like this. See how that arrow goes, which is 53 degrees to the horizontal, 5 centimeters or 5 units. Or we could just take each one and move each object point on the vertex or on the vertices 3, 4. So for example, I could move C to its image point C prime by moving 3, 4. That means move 3 in the X, 1, 2, 3, followed by 4 in the Y, 1, 2, 3, 4. So that is equivalent to moving along this vector here, right? By moving 3 in the x followed by 4 in the y. That moves you from your object to your image. Similarly, I could do b to b prime. I can do the translation by moving 3, 4 again. So let's do 3, 1, 2, 3 in the x. And then we do 4 in the y. 1, 2, 3, 4 in the y to give you b prime. All right? And you can do that for all of them. Let's do that for one more. Let's do that for a. 3 in the x, 1, 2, 3, followed by 4 in the y. 1, 2, 3, 4. So that carries me from the point A to A prime. So basically, if I took in the exam, they give you this, and they say, all right, find the image of this object by moving, by translating with this translation vector 3, 4, right? You could move each point 3 in the x by 4 in the y, and where they line up, you could connect them dot to dot, and you would get your image shape. So this is your object, and this is your image. Another word that they use for object is this word, pre-image. So there's another name for the object. It's also called the pre-image. And that method is what we call the drawing method. There's a method now that you do calculation. So what we do, we write down the object points, we write down the translation vector, and then we could find the image points. And then you could plot the image points if you wanted, right? So the image point for A prime, which would be the image of A, is found by adding 1, 3, and 3, 4 together. So what would happen is this 1 would be added to the 3 to give us 4. And then this 3 here would be added to this 4 to give me 7. 3 and 4 is 7. So you have 4, 7 for A prime. Let's do that B prime. 3 and 3 will be added to 3 and 4. So 3 here and 3 here will give me 6, right? And 3 and 4 will give me 7. So we have B prime. Let's get C prime. 5 and 3 will give me 8, right? And 1 and 4 will give me 5. So that'll go here. And then finally, 1 and 3 will give me 4, right? And to get D prime now, the next component, 1 and 4 here will give me 5. So this calculation, which takes the object matrix that is made up of the coordinates of each one of the vertices written vertically, adding it now to the translation vector they give us, right, gives us the image points. Now, this is a matrix that we form here. It's called the image matrix, right? Image matrix, right? And from this image matrix, I could write down all of the image points if they wanted. What is the image of A, which is called A prime? Well, that'll be 4, 7. But you don't write it vertically because points are written in a coordinate format, which is horizontally. So A prime 4, 7 is really supposed to be written like this here. A prime 4, 7. B prime 6, 7 is really supposed to be written like this if they want the points, right? The image points. C prime 8, 5, look at here, 8, 5. And D prime 4, 5 here, right? So that's how you would do that if you were doing drawing method, right? Move each point 3, 4. Or if you had to do a calculation method, this is a nice way of doing it. You could do each point individually if you wanted, but this way saves space and it's accepted and it's very, very useful and, you know, makes your working a lot more condensed. The final thing we look at tonight is something called an inverse translation, right? Right? And an inverse translation is one whereby we are looking at moving from the image points back to the object points that those images came from. In the original translation, we started with an object and we ended with an image. So I took these, add the translation vector, and I got the image points. Good. In the inverse translation, we do the reverse. We start from the image points and we try to get back the object points that those image points came from. So let's see what that means. If I start with my object points A, B, C, and I add my translation vector, let's call it T, I will end up with my image points A prime, B prime, C prime. That's what we just did. Sometimes they start with the image points A prime, B prime, C prime, and they want to get back to the object points A, B, C. So they tell you, all right, this is my image. These are my image points. Find my object points that this image came from, right? And what you have to understand is that if this is the original format, which is start point plus translation vector equal to end point, remember we always start with that, start point plus translation vector equal to end point. That is your major equation for any translation, right? If you had to get the object points starting with the image points, then a simple algebra could tell you that to get this, all I have to do is, some people say bring it over and change the sign like this, minus t, or minus t on both sides. In both cases, you're going to get this relationship. That is to say, if I have these image points, to get back to this object point, I have to minus the original translation vector. And minus the original translation vector is known as the inverse translation vector. Good? So if I started off with a translation vector of minus 2, 5, which means move each point 2 to the left, that minus means 2 to the left, and then 5 up, then the inverse translation vector, which would take the image points back to the object, is given by minus t. Now minus t means minus on this, which will give you a plus. So minus minus 2 is plus 2. And minus on this, minus plus 5 is minus 5. So if I apply this inverse translation vector, which is 2 to the right and 5 down, it would take my image points and give me back the object points that it came from. If I apply this one on the object points, it would carry me to my image points. So that's what the inverse translation vector. It is a vector that takes the image points and carries you back or gives you back the object points that it came from. So let's see an example of a question like that could be posed to you. In this example, triangle ABC is mapped onto triangle A prime, B prime, C prime with these vertices. A prime is minus 3, minus 2, B prime 3, 1, C prime 0, 4. Under a translation T equal to minus 2, 5. In other words, if I took ABC and I added T to it, I would end up with A prime, B prime, C prime, right? So determine the vertices of the triangle ABC. Well, I could do a calculation, meaning if I have the image points A prime, B prime, C prime, A prime, B prime, C prime, I learned up here that if I have the image points A prime, B prime, C prime like here, and I want to get back to the original object points, which is what they're asking me to do, determine the vertices of the original triangle ABC. Well, according to our calculation, we'd have to take away the original translation vector, which is take away minus 2, 5 from these points, and I would get the object points. So if I took A prime, which is minus 3, 2, B prime, which is 3, 1, C prime, which is 0, 4, right? And I made up this matrix, and I took away from that matrix T, which is the original translation vector. I'm taking away T. So I'm going to take away minus 2, 5 from it, take away minus 2, 5 from it, I will end up with the original object points. That's what we just calculated. So let's do that calculation. So minus 3 minus minus 2, which is the same thing as minus 3 plus 2, will give me minus 1 or negative 1. And then minus 2 minus 5 will give me minus 7. So I would be able to find A from A prime. How do I find B from B prime? Well, I take B prime, which is 3, 1, and I minus the original translation vector from it. So it'll be 3 minus minus 2, which is 3 plus 2. That'll give me 5. And 1 minus 5 is minus 4. So I would now be able to find B now, which is this, from B prime. How do I find C from C prime? Well, if C prime is 0, 4, I have to minus this from it to get C. So let's do that. 0 minus minus 2 is the same thing as 0 plus 2, which is 2. That's this. And 4 minus 5 is negative 1. So it means that from the image points, if I take away the original translation vector, I got the object points, which is what they ask us to do. Determine the vertices of triangle ABC. So A cannot be left like this because for a point, I need to express it as coordinates. So make sure and put it horizontally. So A would be minus 1 minus 7. B, 5 minus 4. C, 2 minus 1. And this would be the answer that they wanted for this question if you had to do a calculation method or they give you a choice. So if they tell you determine, that means you have a choice. You don't have to do a drawing or you don't have to use the drawing. If, however, they didn't give you a choice, in other words, they give you A prime, B prime, C prime on a drawing, or they told you by a drawing method or using a diagram, then it means we have to draw this on some form of graph paper and then find a way to move from the image points and carry ourselves to the object points. So let's see how we would do it. We said that to get from the object to the image, right here, using the translation vector, minus 2, 5 means move 2 to the left and then 5 up. This is not what we have to do. We have to do the opposite. We have to move from the image points back to the object because we start off with the image A prime, B prime, and C prime. So that means we have to use the inverse translation vector, which is minus t, which really is 2 minus 5. That is, take each of the image points and move 2 to the right and 5 down, and that will carry us back to the original object points. So let's do that. 2 to the right, 5 down. So starting from here, I need to move 2 to the right and 5 down. Now, some people would have done 2 to the right like this, 1, 2, and then 5 down like this, 1, 2, 3, 4, 5, which would have landed you here. But that would not have been correct because this scale is a kind of strange scale. If you look here, the scale is 2 blocks. 1, 2 gives me 1 unit. See it there? 2 blocks. 1, 2, that's 1 unit. 2 blocks give me another unit. Same thing in this axis. 2 blocks. 1, 2 gives me 1 unit. Another 2 blocks. 1, 2 gives me another unit. So you have to be careful when you're looking at your scale. And so if I need to move 2 units to the right, it means I have to move 2 sets of 2 blocks because this will be 1 unit to the right. That would have been another unit, which is 2 units to the right. And then if I have to move 5 units down, according to this here, I now have to move 5 sets of 2 units down, like this. That's 1. That's 2. That's 3. That's 4. That's 5. And that's how I move from A prime to A, which means move from the image to the object. And I would have plotted that point there, and that would have given me A. Right? If I wanted to, I could have then measured it, right? Starting here, to get to this point, I have to move -1 in the x, followed by -7 in the y. So the coordinates of this would be -1, -7, which is what I got from calculation as well. Let's find b. To get to b, I need to start at b prime. And then I need to move according to what we said the inverse translation vector will be, which is 2 to the right, 5 down. But remember, 2 to the right, based on this scale, 2 to the right will be this. 1, 2, that's 2 to the right. 5 down will be this. 1, 2, 3, 4, 5. That's 5 down. So 2 to the right and 5 down carries me from the image to the object point, which would be this point here. And if I check that, that's the same as moving 5 across and 4 down. That's 5 minus 4 by drawing method, which is this as well, 5 minus 4. To get from C prime to C, I'd have to move, what it is again? 2 to the right, 5 down. So let's move our 2 to the right. 1, 2, that's, sorry, 1, 2, that's 2 to the right. 5 down, 1, 2, 3, 4, 5. That's 5 down. So that carries me to C, right? From my image point C prime to my object point C. By applying my inverse translation vector, I got here, which was 2 to the right and 5 down, brought me to this point. And what is this point? Well, let's check it. It's 2, -1. So this is 2, -1. Let's see if we got it by calculation as well. 2, -1. So therefore, we would have been able to calculate both by drawing method and by a calculation method. Okay, so that would be it for today's tutorial, right? We started at 6 and we ran to this point. Okay, so this, just like the others, would be put up on our YouTube channel. So if you came in at, a later time, you'd be able to source it from that channel and you'll be able to see all the things that you would have missed if you came in a bit later. All right, I also sent out a multiple choice paper. So have a look at it. We will correct that soon. And then we will be doing some paper 3-2s as well. All right. So that's it for tonight. I will see you guys in the other class where we will do session 8 and close off our sessions. Okay. So God bless, and I'll see you guys in the next class.
You too, sir.
All right. Take care.
Bye, sir.